and topological quantum material in today's talk. You can see here the title of my today's talk is Topological Quantum Material and Transverse Thermoelectrics. So I'll try to cover it in three parts. So I'll talk about topological quantum material. What is thermoelectrics? We should know basic thermoelectrics and what is the disadvantages there. And then we'll start the transverse thermoelectric, where topological quantum material can act as a important candidate. So first 1 hour, let's learn about quantum materials and their thermoelectric properties. So now first question you can ask, what is thermoelectric? And it can see here, this is a longly discovered in 1882, that is the Seebeck effect. So if you have one metal A and metal B, now you connect them and in one side you give temperature and one side it's not. So there is a temperature gradient. So you can measure voltage out of it. So the thermoelectricity depend on this Seebeck effect, which is a direct conversion of temperature gradient into electrical voltage or vice versa. So how thermoelectric device look like? So let's take a p-type semiconductor and n-type semiconductor, and then you have to connect electrically in series and thermally in parallel. So if you give one side hot and one side cold, you will get electricity. Now, whatever material you prepare for the application, you cannot make device because it will be cost expensive and it will take you lots of time. So whatever material you prepare, we need to filter them out. Now, how we filter? For that, we call a parameter thermoelectric figure of merit. And this is a purposefully a dimensionless parameter. So you can easily compare from one material to another material. So this GT depend on electrical conductivity. So how fast or slow carrier can move from, let's say, one side to another side. This is the Seebeck coefficient. That is the change of the voltage with respect to the change in the temperature. And another one is the thermal conductivity. Now we know from our solid state chemistry or physics knowledge is that metal will have a very high electrical conductivity because it has a free electron. And at the same time, glass will have low thermal conductivity. Now, why we need property of both metal and glass? If you see the formula of ZT, the numerator you have electrical conductivity and the denominator has thermal conductivity. So if you need a high ZT, you need high power factor or low thermal conductivity. Now, this is the challenge in this field to prepare a single material where you will have contribution from both metal and as well as the glass. And this is the most challenging in this thermal. Now, as a solid state chemist or physicist, you can design a material where you will have a property of both metal as well as the glass. Now, what is the importance of thermoelectric? Why you should do research more on thermoelectric? Because if you see the total energy consumption chart with respect to India and world. And at the current scenario, you can easily correlate that we are still depending on coal, petroleum, and biomass waste for our daily purposes. Like if we want to use power plant, automobile factories, we are still depending on those non-renewable energy sources, and it emits CO2. And you will be more surprised by knowing that whatever energy you are using for daily purpose, you are losing 65% of that energy as a heat. So let's say if you run a car for a with 1 liter of petrol or diesel, so you are using only 65% energy is losing as a heat, and only 35% is actually using by the engine to move it. So what is the fate of that waste heat? Now, if we can convert at least 10 to 20% of that waste heat to some useful form, it will be huge impact to our society. And thermoelectric material do exactly same. It convert this waste heat to electrical energy. And this thermoelectric people are using from the long time in 1976. NASA used that. After that, people started using for watch, and the car company BMW they also use. So what the car company or bike company they do, you have an exhaust and that temperature is high. So now if you put the thermoelectric device on it, so is one side is the hot and another side is your environment temperature. So you basically get a temperature gradient and you can get electricity out of it. And BMW using this concept to run the AC or to get a seat warmer. And future also that you can use maybe with the biological system, so it can be more useful for our daily life. Now question is how to design a material, right? So now for that we have to look to our best man-made table, that is nothing but our periodic table. Now if you move from top to bottom of the periodic table, you can see the mass of the atom will increase. That means they will heavy. So they can act as a glass because then they will vibrate less. So when electron will transfer or the heat will transfer, they can scatter more. So it will decrease the thermal conductivity. Now at the same time, if you take let's say lead and if you take oxygen, lead oxide, it has a huge band gap of 2.5. But when you move from oxygen to tellurium, my electronegativity will decrease, so the band gap will also decrease. This can be seen from simply a MO diagram. For lead oxide, let's say you have a huge band gap which acts as an insulator, but if lead telluride, it acts as a semi-metal. So that means if you want to use the material for thermoelectric, it has to be heavier or highly doped narrow bandgap semiconductor. And that's why people say either lead telluride, germanium telluride, or bismuth telluride is a good candidate for thermoelectric applications. Now, in soon we'll say that why topological material also comes in the picture. Because I'll come to topology in a minute, but as you know that in topological material, you need a strong spin orbit coupling. So you can get a band inversion. So at the same time, you need a low thermal conductivity and highly Seebeck coefficient. So all this property can be satisfied if we choose a heavy element with large atomic mass. It will give me a strong spin orbit coupling as well as low thermal conductivity. And now if I choose a narrow bandgap semiconductor, it will be easy to give me a band inversion at the same time give a high Seebeck coefficient. So that's why topological materials are also a good candidate for thermoelectric applications. Now what is quantum material? And I'm sure that most of us watch this Avenger Endgame and we all like that because they use the term quantum realm. So this allows the basic law of physics to be broken in a largely fantastical way. Now, after saying that, or in a current scenario, you can also ask a very simple question that do you guys just put the word quantum in front of everything to make it sense in the current scenario? Can we hold something quantum material? Does it make any real sense in our real world today? So actually, you know that now quantum materials are not just a plot device of sci-fi movie, because in reality we are already using quantum material in our daily life. Now, if we go to hospital for a MRI, people use superconductor. That is a quantum material. Now we are using hard disk drive to store our data and which use giant magnetoresistant sensor. These all are the applications of quantum material. So that's why we can say in a broader aspect that quantum materials are refers to a rapidly evolving research frontier that have a three aim. First, to understand. Second is the control, and third is the design of material in which quantum physics enable novel functionalities. Here I have summarized few quantum materials like topological insulator, wire semimetal, superconductor, and so on. Now, if you put quantum materials as a keyword in the Scopus, you will see the number of publication increases with years. Which what does that indicate? This says that people now try to understand that quantum materials are the future for all the practical application in near future. And you can see here in this field, we have more Nobel laureate in this. And as a result, our government also launched a national quantum mission with the allocated budget of approx 6,000 crores. Now, after that, we ask a very simple question. Can we use this quantum material for energy applications? Because there is a strong interaction between spin, charge, and lattice. And it will open a new door for energy or related applications. Now you can see this energy tree. It can be used in different energy sector, but in today's talk, I'll mainly cover thermal electricity. So in this one, in this nice review by Nitesh Kumar and Claudia Filzer group, they have they have made a nice review and say that you have a different kind of topological material and it can have a wide range of application from quantum transport, quantum computer, photovoltaics, catalysis, thermoelectric and so on. Now come, what is topology? Maybe you all know this slide, but this is one of my favorite slide I'm using maybe for from my PhD, this same slide. This topology is a study of geometrical properties that is unaffected by the continuous change of shape or size of the figure. You can see that this coffee mug can be easily converted to a donut, and they are topologically equivalent objects because the number of fold in both the scenario is 1, that we call G equal to genus. But if you look at the donut and orange, although both are eatable, but topologically they are non-equivalent. Because in donut you can see the number of genus or hole is 1, but in orange it is 0. Now the question, from where the topology come in chemistry? Because I am coming from a chemistry background, so it will be easy if we can correlate with the chemistry as well. So whenever we talked about any aromatic compound, we immediately think about a benzene ring. This is a C double bond C and then C single bond C. Now this is a famous Kekulé structure. Now if we look at there in more detail, you can see that the pi electron delocalized throughout the benzene ring. And from the MO diagram and the electron count, we can say that this is a aromatic system which follows the Huckel's formula of 4n plus 2 pi electron. But let's say you have a ring of 8-member ring. So according to this Huckel formula, this is anti-aromatic. Now why we are talking about benzene? Because this is can think about the structure of graphene, which is a condensated benzene, and the structure is also aromatic. Now, this is the advantage of organic chemistry. So, in this paper, they have shown that they can easily twist the bond to make the donor to the Mobius strip without breaking and making any bond. But in simply, if we take a paper and we want to make the donut into Mobius, we have to cut one bond and then you have to rearrange again. Without that, we cannot. But aromatic ring can be easily twistable and then it can change its topology. But in solid material, we cannot do that. So where does the topology comes in material picture? So from our, again, from the physics or chemistry knowledge, we know that materials can be classified in either metal or semiconductor or insulator depending on the gap. Now in metal, there will be overlap between valence band and conduction band. And in semiconductor or insulator, there will be gap between valence band and conduction band. As a result, one can conduct electricity and one cannot. So where does the topology comes in this picture? Now to understand that, take a simple example of valence band and conduction band. Now if the interaction is strong, they will overlap. So if these crossing are symmetrically forbidden, they will open up. That is easily understandable. But in some materials, they are symmetrically allowed. So ideally, they should not open up the gap. But if you look at the real scenario, you will see a opening the gap. So because of the strong spin orbit coupling, it open up the gap. And now as a result, you can see Your valence band has a contribution from conduction band, and your conduction band has a contribution from valence band. And this gives rise to a new classification of material in topological insulator. So in this, there is a topological insulator term. In this material, in the bulk, it acts as a insulator where you have a gap between valence band and conduction band. But at the surface, it acts as a metal. There will be no. Now, why we are talking about topological material? What is the importance of that? Because they have a very robust surface state and the surface modification is not allowed. So we can get scatteringless transport along the surface. So now we'll talk about different classification of topological semi-metal because we'll go to the application part with a particular classification of topological semi-metal. So after the band inversion happen, if you have a strong spin orbit coupling, one scenario can happen. It open up completely between valence band and conduction band. So there is a gap. And those material we can call topological insulator. But in some material, they will not be completely opened up. So there will be two touching point which still they have a valence band and conduction band crossing. And depending on that crossing, either it is a point or it is a line or ring, we can call either Dirac semi-metal or we can call nodal lines. Now in Dirac semi-metal, all bands are doubly degenerate because you have a upspin and you have a downspin. So you have a 4 band, so that's why we call doubly degenerate. Now if we can break this degeneracy either by time reversal symmetry broken or inversion symmetry, it can open up and you will get a singly degenerate wild semi-metal. So I'll talk about more specifically few more different classification of topological insulate quantum material. So one most fast discovered is the topological insulator. Here you can see the requirement, you need strong spin orbit coupling and the number of band inversion. That is very important. If you look at any topological material, the band inversion mostly happen at the gamma point in the Brillouin zone. And the number of gamma point in the Brillouin zone is odd number. That's why we call topological insulator the number of band inversion is in the odd number. And the metallic surface state protected by time reversal symmetry. And there's another classification of topological material that is topological crystalline insulator. Now, how it is different from topological insulator? You can see here the number of band inversion that is even number. And the metallic surface state is protected by here crystal mirror symmetry. So these two are main difference between topological crystalline insulator and topological insulator. So Bi2Ac3 or Bi2T3 is a well-known topological insulator, whereas tin telluride is a well-known topological crystalline insulator. Now, for a few minutes, I'll talk about particularly this composition Pb.6 Sn.4T. Now, if you look at the band diagram of PBT and SNT, you can see here PBT valence conduction band and tin telluride valence band. They're made of similar atoms. So now if I dope slowly tin in lead telluride side and in that lead rich region, you will get this kind of composition. And previous theoretical calculation as well as the experimental result, this suggests that this material is also a topological crystalline insulator. Now the problem is that in this material, the bulk band gap is less than 5 millielectron volt. So that means this is not a good material for thermoelectric application because we need narrow band gap, but not less than 5 millielectron. So previous literature says that if this material, if you have a structural distortion, it can breaks this mirror symmetry and it will open up the band gap. So physical perturbation can easily open up the gap and it can have a different applications. That's why we thought, can we use simple chemical doping strategy? Because again, when you talked about physical perturbation technique, you need either synchrotron based HTM or angle resolved photoemission spectroscopy. So you need special expertise to do that. So we thought, can we use simple chemical doping in the lab-based technique? Because chemical doping can give rise to a perturbation to the local crystal symmetry, and it can modify the electronic structure, and it will enhance the thermoelectric properties. With this motivation, we have choose sodium as a dopant. Now, this is the most important result. You see here, the black curve is the band gap of PbSNT material. And you can see there's a no gap. But as soon as we dope sodium, you can see there's an enhancement in the band gap. What does that indicate? That means whatever we thought that chemical doping can break that mirror symmetry and open up the gap. Actually, sodium is doing that. Now to confirm that, we did theoretical calculation. So with Professor Webb.
Hello, hello. Dr. Subhajit. Uh, I think there seems some problem. I can't hear you. Yeah, hello everyone. We are trying to connect with the speaker. Somehow it seems the network problem is there. So as soon as we connect, he will be again online. So stay there. We are trying to connect with him. Mm. Yeah. Hello, everyone. I just had a talk with Professor Subhajit. He is joining again. So he could not see that he is offline. That's why, and also he was not picking up the phone.
Yes, so
So
I
he,
didn't realize.
so yeah, he's
So
joining
up,
now.
yes, can you see me now? Yeah, is it visible?
Yes, you are
Uh,
visible now.
Acha. Yeah, because I didn't realize that I do not have network here. So up to what slide number, or can anyone say that it is visible? Then I can start from the next, maybe after 5 minutes break. Because I was speaking for half an hour, but it was not visible. Yes.
yes, sir. We can take a break here, and then we can restart.
Yeah, from maybe 4 p.m. after just 5 minute break.
Sure, sure.
Okay, thank you. Yes.
Yeah. Yeah, sure.
Yeah, so maybe I can share one more time and please someone let me know up to what I was visible or audible. Then I can brush up slowly and very fast, and then I'll talk about mainly transverse one. And
Yeah,
yeah,
possibly you were talking on anodode, PBS, and TE.
oh, acha. Okay. I'll just cover. Maybe we can start, right? So I'll just share.
Yes,
Maybe.
yes.
So maybe it was visible up to here. Point.
Uh,
So,
can you
so
scroll little more uh, forward? More forward? No, I think we need to go backward.
this thing is audible, right? Yeah.
Yeah, this was audible. Further, also audible. Yeah.
Maybe I can start from here. Maybe I'll just go through quickly and then.
Yeah, you can start from any subtopic nearby.
Yeah. Yeah.
Yeah.
So, welcome. Good afternoon, everyone. And really sorry, I didn't realize that my mobile was on silent. So, what I was talking about that PBSNT, want we want to work on that, and it has a very less band gap. So we want to break the mirror symmetry to open up the gap so we can use for thermoelectric. So for that we choose purposefully chemical doping because it can open up the gap by modifying the electronic structure. So that's why you can see here whenever we dope sodium, it can increase the band gap. This gives a simple uh, idea that it open up the band gap by breaking the mirror symmetry. This is also confirmed from the theory that when we dope sodium and retain the mirror symmetry, there is a no opening in the band gap. But when we dope sodium and break the mirror symmetry, it open up the gap. And now we measure thermoelectric properties, both Seebeck and as well as thermal conductivity. You can see here for the pristine sample, the Seebeck initially increases and then decreases because it has a narrow band gap. So we are getting bipolar contribution, which is not good for thermoelectric. But with sodium, as the band gap increases, the Seebeck coefficient increases. As a result, with the sodium doping, we got a good ZT of 1. Now, to generalize the concept of chemical doping, we choose another doping, potassium, and it also increased the band gap, which was also confirmed from the theory. And at the same time, we can improve the ZT compared to the pristine sample. Now, whatever I showed maybe in the first few slides, if we look at thermoelectric device, we need both P-type as well as N-type material. So in previous work, we got P-type material. Now, what about N-type? And it would be always good if you can make the P and N from the similar material because of the compatibility. So for that, we purposefully choose iodine in PBSA. And as a result, you can see iodine again act as a chemical dopant. So it breaks the mirror symmetry and open up the gap. But at the same time now iodine moves the Fermi level to the conduction band. As a result, we observe a negative Seebeck which indicates that now electron is the major carrier. At the same time, like previous way, we observe a good thermoelectric figure of merit in iodine dope sample. So now we can say the chemical doping strategy is very good effective way to improve thermoelectric properties of a topological crystalline insulator. Now we'll talk about another topological crystalline insulator material, that is the tin telluride. But tin telluride is not a good thermoelectric material because it has a very high carrier concentration, high lattice thermal conductivity, and low Seebeck coefficient. So it does not satisfy a single condition to be a good ZT material. Now, to how to work on that? So first, we have to increase the Seebeck coefficient. For that, we can choose either resonant level effect. Now, how to get understand that? Now, if you have a large change in the slope near the Fermi level, you have a large Seebeck coefficient according to Mott equation. And if you have a small slope, so you have a lower Seebeck coefficient. You have to choose the doping according to that. Now, another concept is the valence band convergence. In tin telluride, like similar way, you have a light hole valence band and you have a heavy hole valence band. Now they have a large gap. So contribution from the heavy hole is really low. That's why Seebeck is very poor in tin telluride. Now, if you dope some material with a heavy band gap or a high band gap, the primary gap will increase and this gap will decrease. So as a result, you will have a valence band convergence and large Seebeck coefficient. With that thought process, we have mainly worked again on that SNT PBT regime. And here we thought, can we use synergy of co-doping? Indium will act as a resonant level doping near room temperature, and magnesium will act as a valence band convergence at the high temperature. With this thought process, we measured for Seebeck for the pristine sample. Then we dope for the magnesium, it increases because of the valence band convergence. At the same time, we observe for Indian doping, room temperature, there is a huge enhancement in the Seebeck coefficient. Now, when you co-dope sample, you can see it outperform all other singly doped or pristine sample because of the co-doping of valence band convergence as well as resonance level formation. This is also confirmed for the theory as well. As a result, we observe a GT of 1 in tin telluride based system. But till now, we didn't talk about thermal conductivity part. So you can see here the K minima, that means that is the minimum thermal conductivity you can achieve in tin telluride. But the thermal conductivity is quite high, approx 3 watt per meter Kelvin. Now, how to overcome that problem? So there are many study people have done, but no one could reach the minimum thermal conductivity. That's why we took a three-step strategy. First, reduction of carrier concentration, then reduction of K lattice by tin selenide and tin sulfur, and then enhancement of Seebeck again by co-doping. So by doping selenium and sulfur, we measure the thermal conductivity, and now you can see here thermal conductivity reaches the minimum limit. And now we want to understand what will be the reason for the minimum thermal conductivity. So when you dope 2 or 3 elements in one crystallographic site, the configurational entropy might increase and it will decrease the thermal conductivity. To confirm that, we calculated the configurational entropy with help of Professor Shapanpati's group, and we observed, yes, indeed it increased the configurational entropy in the system. But when we look in more deeper way, and when we fitted our data with Clement's model, so what this model physically says that if the only configurational entropy is responsible for decrease in thermal conductivity, so the measured thermal conductivity follow this trend. You can see pristine data follow the curve, but our measured data do not support that. What this indicate? This indicates that we have some other mechanism than the point defect. Then we look at the phonon dispersion of tin telluride much more in a detailed way. And we observed several flat, negative or imaginary phonon mode coming from sulfur atom. What that physically means? It indicates that sulfur atom off-centered from its own position. Now to confirm that, we did pair distribution function analysis. So this is a total scattering technique. So it will give you a global information like lab-based X-ray. At the same time, it will give you information about the local bonding. So in tin telluride, it will give a cubic structure, But locally, we observe sulfur off-center experimentally as well. And then next step, we dope co-doping silver and indium. As a result, we observe large Seebeck coefficient and a high GT of 1.3 in tinted red-based system. And in the current review, they have summarized the advances and challenges in tinted red-based system. Now you can see with the several years of research, now people reach 1.9 GT in tinted red. But that is still not sufficient to overcome lead telluride. Because in this plot you can see all the lead telluride based material shows a GT more than 2. But we know the toxicity of lead. So all we need lead free high performance thermoelectric material. So in 2014, tin selenide created a sensation in this thermoelectric field because it shows a very high GT in this range and with a 2.6. But the main problem with tin selenide is that it observes only in a single crystal. But if we want to make the device, we need to make a polycrystalline sample. So we ask a simple question, can we realize this much large GT in a polycrystalline sample? So we purposefully worked on silver antimony telluride system, which also has a Roxol structure like lead telluride. But this material has several advantages compared to lead telluride. You can see here the thermal conductivity of this material is close to zero point 0.5 watt per meter Kelvin, close to the glass limit, whereas the lead telluride close to 8. Now, why it is so low? Because the antimony or bismuth has a inert lone pair effect, 5s2 or 6s2. Actually, it can create a strong enharmonicity in this system and it decreases the thermal conductivity. And at the another advantage is that it is a favorable valence band. You can see here it is a multiple valence band at the same time very flat. So we can get a very high Seebeck coefficient in this system. But when we look at the literature and studied more about this system, we observe experimentally to be always disordered silver and antimony. But theoretical calculation says that if we can realize the ordered state, we can realize very high thermoelectric figure of merit. So we ask, can we realize this ordered state experimentally? So then we want to first understand what is the importance of this ordered disordered state. Now, if your system has a strongly disordered system, it will create a strong localization, like Anderson localization. So you will get a very low electrical conductivity now because it is an insulator. But at the same time, if you have a very high disorder, you will have a localized state and it will distort your density of state. So we can get high Seebeck coefficient. So we have to tune the Fermi level in such a way that we can get high Seebeck coefficient as well as high electrical conductivity. With this, we first want to understand why experimentally we cannot stabilize the ordered AGSBT2 because there is a large size mismatch as well as charge mismatch. So we purposefully choose cadmium 2 plus because it has an average size between silver plus and antimony 3 plus. At the same time, its charges is plus 2, which is also average. With this motivation, we have synthesized this material and then we perform all the measurement. Now we measure the Seebeck coefficient low temperature. Now you can see here for the pristine sample, we observe a large Seebeck coefficient. That means it has a strongly localized state which come from the disorder. Because it is already reported that pristine sample will have always silver and antimony in disordered state. But when we dope cadmium, you can see the excess Seebeck coefficient vanishes. That means the delocalization happened with cadmium doping and it decreases the Seebeck coefficient, which is also confirmed from our theoretical calculation that cadmium doped at the antimony side and increases the ordering in the system. Then we want to visualize that by using TA. So first we did pristine AgSbT2 and we didn't observe any ordering in the pristine sample. But when we did the same for the cadmium group sample, we observe a nanoscale superstructure formation as well as cell doubling due to cation ordering. So this all gives the indication of cation ordering in the cadmium group sample. Then we measure the thermoelectric properties. First, we measure thermal conductivity. And you can see here, although pristine sample is quite low thermoelectric, but with cadmium doping, it decreases further because it has a nanoscale superstructure as well as anharmonicity in the system. Then we measure all other thermoelectric parameters, and most importantly, we observe ZT around room temperature is 1.4 and at 2.6 at high temperature. So we realize polycrystalline sample that much high ZT. And then we compare where we belong with respect to the wall. And you can see our material outperform all other material from low temperature to mid temperature region. And then we fabricate the thermoelectric device in our lab, and which gives indication of around 10% conversion of heat to electricity. So now comes why the transverse thermoelectric is important. Because the conventional CBEC device require P and N type, which has to connect electrically in series and thermally in parallel. So as a result, as you see, we'll get always lower experimental efficiency than the theoretical efficiency. Now, how to overcome that? For that, there is another technique or method we call transverse thermoelectric or nernst effect. Now, let's see how to understand. So, let's say you have a single material. One side is hot, one side is cold, similar to Seebeck effect. But here you are applying a magnetic field perpendicular to this heat current. And as a result, you are getting a transverse voltage under this temperature band. So this is the simple geometry of non-stiff, and it has several advantages. You don't need complex electrical connection, you do not need a contact resistance, and no need to make a p-type as well as n-type material. Now, how to understand the Nernst voltage? So for semi-metal, this is the Nernst coefficient. Although you can see this is a large equation, but the main thing, it depends on the mobility of both electron and hole as well as their the transverse voltage. In this aspect, topological semi-metal are good candidate because semi-metal will have both p-type as well as n-type carrier, and it will have very high mobility. Now I'll use a term that is the Berry phase and curvature or Berry curvature, because from the next slide we'll use this term many times. So what is Berry phase? Actually, this is a geometrical phase, and it is first introduced by Sir Michael Berry in 1984. And in this Berry phase, it indicates the global change without local change. In thermoelectric, we are mainly talking about local change without global change. But in Berry phase, it talks about global change without local change. Now, how to understand Berry phase? Let's talk about this circle. This is North Pole. This is my South Pole. Now I start from here. Now I have one arrow. So it always pointing towards south, north to south. So we start the moving, the spin or direction without changing the direction. Let's say I start from here, go this way, and then I complete the loop. So now you can see where I start and where I end. There is a gap. There is a geometrical phase. That's the angle phi. So this is the geometrical phase, and this is known as a Berry phase. So this Berry phase can be calculated by line integral of potential, which can be termed as Berry potential or Berry connection in a closed loop. It has to be a closed loop. If it is not closed, then you will not get Berry phase. And The Berry curvature you will get from the surface integral. But what does that physical mean of Berry curvature? It can be viewed as an effective magnetic field in momentum space. Now, why we are talking about Berry curvature or Berry field? What is the importance in topological field? Because it will be help you to say or calculate the topological charge. It can say this is a topologically trivial material or topologically non-trivial material. At the same time, Berry curvature can be used to compute intrinsic anomalous Hall conductivity or anomalous Nernst conductivity in a ferromagnetic material. So we talked about Nernst effect like conventional Hall effect. Similarly, if we can include the band inversion or by including the magnetism, if we can get a large Berry curvature, we can get a large anomalous Nernst effect. So we'll come to this later soon. Now question how to design material for the anomalous Hall conductivity or anomalous Nernst. In this one, we can believe or we can depend on the lattice model. So most famous one is the honeycomb lattice. It shows a Dirac point between valence band and conduction band. There are several other lattice like dice lattice or square net lattice, but one of the most important lattice is the Kagome lattice. What is the importance of the Kagome lattice? Now first let's understand what is the Kagome lattice crystal structure. The Kagome name came from the bamboo basket woven pattern in the Japan. So you can see here it is a combination of triangular lattice as well as a honeycomb lattice. Now honeycomb lattice will give you the Dirac point. So now what is the role of triangular lattice? It will give you a strong frustration in the system. So it will have a huge impact in its electronic structure. Now when you look at the Kagome lattice, it is a Dirac point, band of singularity as well as the flat band. Now, if we can introduce strong spin-orbit coupling or magnetism, it can open up the band gap and it will have a several application in magnetic Weyl fermion, Chern physics, and so on. And another aspect is that if we can move this Fermi level either in band of singularity or flat band, it will have huge density of state. As a result, we can get superconductivity, nemacity, CDW, anomalous Hall or Nernst effect. That's why we can say that Kagome lattice can be an ideal platform to study between the frustrated geometry, correlation, and topology. Now we are coming slowly from topological insulator to magnetic topological insulator. Now the question is why we need magnetism? Because magnetism will break the time reversal symmetry and it will open up the gap. Now if we can tailor the Fermi level inside the gap, we can realize quantum anomalous Hall effect or quantum anomalous Nernst effect. Now this quantum anomalous Hall effect, previously people achieved only by doping magnetic element in a topological insulator. But it has a several disadvantages like fabrication, measurement, property optimization, and so on. So what is the alternative? We have to think about something intrinsic and stoichiometric magnetic topological insulator. It can be either antiferromagnet or ferromagnet, and we have to synthesize very high good quality single crystals. Now, as you all aware of the Hall effect family, but I'll just quickly go through that. So, ordinary Hall effect first discovered in 1879 by Edwin Hall. So, what he did, so this is a single material, and now I apply the current and magnetic field perpendicular to it. So, I'll get a transverse voltage due to the Lorentz force that is known as ordinary Hall effect. Now, if my system is a ferromagnet, so the magnetic spin will be oriented in one direction. So when current move along that, it will have an extra contribution to Hall that is known as anomalous Hall effect, and it was discovered in iron in 1881. And after that, recently there's another Hall effect discovered if I have a non-coplanar spin structure and my current flows. So that non-coplanar spin structure can also affect my Hall effect, and it will give a extra contribution that is known as topological Hall effect. So now if we can realize large anomalous Hall effect, it will have a huge application for the low power consumption and high speed electronic devices. At the same time, if we can realize large topological Hall effect, we can use that for data storage applications. Now I'll come the very important part of the topological quantum material is the synthesis of single crystal. So whenever you want to synthesize some material in your lab, so first we have to look at the phase diagram because that will be act as a guiding map. So first phase diagram, either it can be incongruently melting. That means if we go to the liquid state and come back to the solid state, you will not get proper of your ideal compound. You will get mixture phase. And another case, you can see if we move from liquid to solid, you will get of your composition. That we call congruent melting. Now, depending on the phase diagram, you can choose different crystal growth mechanisms. So in this talk, I'll mainly focus metal flux method, chemical vapor transport, and Bridgman method. So if it is an incongruent melting, you can choose metal flux growth method. But you cannot use Bridgman or CVT. For that, it has to be congruent melting material. Now, you might already know this all the method. So I'll go through very quickly. So Bridgman is the most widely used one, and you can see here centimeter long single crystal of topological quantum mechanics, and it is very easy to use. So one side will be hot, one side will be cold. Now you slowly move from hot to cold side, and after a certain temperature, this cold zone will start forming the crystal, and then you slowly pull down this direction from hot to cold, and your crystal will grow along this direction. And another technique is the metal flux growth method. So in this method, what you have to do, let's say you want to synthesize some material with manganese, cobalt, iron material. But in our lab, we are mainly using uh, quartz tube, which can go minimum or maximum 1100 degree. So how to synthesize this material? So what you have to do, you have to take excess low melting metal as a flux. So that act as a solvent. So let's say we are talking about MnBi2T4. So we have to take excess bismuth telluride, and it will first melt around 450 or to 650 degrees centigrade, and after the reaction you have to centrifuge the excess liquid at high temperature, so you will get ideal crystal of your requirement, and you can get large crystal by using the uh, uh, this metal flux technique. There is another one is the chemical vapor transport. So what you have to do, you can put a material, let's say J.T5, and you put iodine as a transporting agent. So it will move from either hot end to cold end or cold end to hot end, depending on the it is exothermic or endothermic reaction. And you can get a good quality large crystal. And the best part here is that you don't add any extra metal. So there will be very less possibility of impurity in the crystal. So you'll get very high mobility single crystal of topological quantum material. So I have already discussed this quantum material output for thermoelectric applications. Now I have already talked how to improve the Seebeck coefficient, either resonant doping or valence band convergence. Now what we can do in topological material, we can increase by applying magnetic field. Now what is the advantage of magnetothermoelectric effect in topological material? So it will have a large density of state distortion by applying magnetic field. So it can improve my Seebeck coefficient. At the same time, topological semimetal will have both p type as well as n type. Now, with applying magnetic field, they'll move both in same direction. So you will have a additive direction to a Seebeck effect. This is just an overview. I'll come one by one. You can see here there is a huge enhancement in the Seebeck or thermal power. That is the non-thermal power of 7,000. Whereas in conventional lead telluride or germanium telluride, you can achieve only 200. That because it has a high mobility, it is a wild semimetal, and it has a compensated electron and hole in this system. So now come one by one example to understand the effect of topological semimetal on transverse thermal. So first example you can think of WT2. So this is a perfect electron hole compensation in the Fermi level, and it has an ultra high mobility of 10 to the power 4. And as a result, you can see is a huge magnetoresistance observed in this material. And this is a van der Waals material, and it can be easily make a flexible or wearable device. As I have discussed already, you can see this is a electron and hole almost similar throughout the temperature range, the value, and the mobility is quite high, close to 10 to the power 6. As a result, when they measure the non-state effect, they observe very high compared to the Seebeck effect or other compared to the other conventional Seebeck. So this is the transverse thermopower and this is the conventional. You can see how much high you can realize in topological semimetal. I'll talk about another material that is the NbSb2. This is a monoclinic structure and this is the single crystal. So it is also a nearly perfect electron hole compensation. That means it will be also a topological semimetal and it also has a high mobility. As a result, when they measure the Seebeck effect as well as the Nernst effect, you can see Seebeck when they measure in topological semimetal, it is only 20 microvolt per Kelvin because your electron and hole will move opposite direction. But in application of magnetic field in the perpendicular direction, they will move in similar direction. That's why you can see how much large Nernst thermal power you can realize compared to the Seebeck effect. As a result, they observe large GT as well as the large power factor in this sample. But till now we are talking about only non-Stefan. So we need to apply a very high magnetic field of 9 Tesla. So can we realize this thing in ferromagnet where we no need to apply that much high magnetic field? So that's why people worked on cobalt 3 tin to sulfide 2, which has a Kagome layer of cobalt and it is a hard ferromagnet. And then they did the theoretical calculation. You can see here several crossing near the Fermi level and it gives rise to a strong Berry curvature in this system. And similarly, they observe a large anomalous Hall conductivity as well as large anomalous Nernst conductivity. Now, the best part of this material is that we can observe they realize zero field Nernst thermal power. That means if the field is zero, you still can get large thermal power in this material. So if this is a list of ferromagnetic material which shows large uh, thermal power, Nernst thermal power by using Berry curvature as a method. Now there is another famous ferromagnet that is the CO2 So this is also a Heusler compound. So there are several crossing near the valence band or near the Fermi level. And they also realize very large anomalous Hall conductivity. And from the theoretical calculation, it was observed that this is mainly arises due to the Berry curvature near the Fermi level. Then they measure the Seebeck coefficient. And the important part of this material is that this material shows large non-effect at room temperature. At room temperature, it is close to 7 microvolt per Kelvin. Now, when they observe that the CO2 MnGa does not follow the conventional ferromagnet. So because this blue shaded line, if it follows, that means it is just simple ferromagnet. I have a magnetism and I'm getting the anomalous Nernst effect. But you can see here CO2 MnGa does not follow that. This gives that it has a very curvature contribution in this material. And that was confirmed from theoretical. This is the Berry curvature calculation, and then they calculate the anomalous non-conductivity. Similar to that, there is another report by Nakashuji's group. They worked on Fe3X, that is the gallium or aluminium, and they also realized very large non-thermal power at room temperature. So whenever we are looking at the literature for the anomalous non-spark, people mainly work on ferromagnet because it is easy to get magnetization. Now, what about antiferromagnet? If we choose antiferromagnet over ferromagnet, it will have several advantages, right? Because in ferromagnet, you will get always low mobility and you will have a strong inherent stray field that can strong magnetic disturbance. But if you choose antiferromagnet, the ferromagnetism originating from the canted spin structure is really weak and it can have large mobility. So that's why when you look at the literature from Claudia Fels's group, this is the first report of antiferromagnetic material which shows a large anomalous Nernst effect in YBMNPI. So in this material, they observe that you have a manganese triangular lattice, and in that you have a canted phase. So canting can give rise to a magnetism. As a result, they observe large anomalous Hall conductivity as well as large non-thermal power in antiferromagnet sample. And that is also coming because of the Berry curvature contribution in this topological semimetal. As a result, they observe very high ZT in this YBMNBI to compare to any other literature for the transverse thermoelectric figure of merit. Now, as I've already told, the advantage of antiferromagnet to ferromagnet, but our goal or everybody wants to apply for room temperature application. So when you look at the literature, it has either high value at low temperature or low value near room temperature. Now, how to overcome that? So that means we need an antiferromagnet material with nil temperature above room temperature, and it has to be a canted antiferromagnet. So we can get a very curvature contribution, and we have to grow very high quality single crystal. So when we look at the literature, we find it out that YMN6SN6, it is a magnetic Kagome layer made of manganese atom, and it has a nil temperature around 330 Kelvin. And the previous RP study showed that it has a Dirac cone and flat band near the Fermi level. This gives the indication that this material or candidate might be good for the room temperature Nernst effect. Then we measure the Seebeck effect, and you can see here throughout the temperature range, Seebeck is positive. That means hole is the major key. Now the most important result comes when you look at the magnetization data. You can see there is a sudden change in the magnetization data. And previous neutron study confirmed that it has a change the spin structure from distorted spiral to transverse conical spiral to fan-like and then force ferromagnetic. And that you can also see in our Seebeck data. We can track that transition. And then we measure the non-thermal power. We observe maximum at 2.4 and room temperature 2 microvolt per Kelvin. Now, as I have mentioned, if the conventional ferromagnet is origin for the anomalous Nernst effect, it will be follow the magnetization. And as a result, we should expect value of 0.5, but we are getting 4 times higher than that. So how to explain that? And then we also calculate the transverse thermoelectric conductivity. That also does not follow the magnetization. This gives the indication we have a different mechanism. And then we did the band structure calculation, and we observed that the presence of non-zero intrinsic Berry curvature near the Fermi level, and that is the reason for realizing the notched effect in this material. And then we compared with previously ferromagnet and antiferromagnet material, and we observe our material or this YMN6SN6 outperform all other antiferromagnetic material, and it can be compared with the ferromagnetic system. Now we are talking about Weil semimetal. So now how we can realize, either we can break the inversion symmetry of the Dirac semimetal, or we can break the time reversal symmetry. So if we break the inversion symmetry, we will get a minimum number of Weil 0.4. But if we can break the time reversal symmetry, we can get magnetic Weil semimetal with a minimum number of Weil point, that is the 2. So you can see this left side image. Near the Fermi level, you have several crossing. So whatever property you are getting from your material, it is very hard to conclude that is coming from the Weil point. But if you look at the very clean band structure in the right side, you can see there is a no other band crossing, no interference of other band near the Fermi. So that's why this system we call ideal Weil symmetric. So what is the possible candidate for that? So when we look at the literature, we find it out. The possible candidate is the ferromagnet UCD2AS2. Now, when we look at the literature, we observe it has an antiferromagnetic structure. Now, how to stabilize the ferromagnetic phase? So we took a leverage of the chemical tunability of this material, and we synthesized the ferromagnetic phase at room temperature by using simple salt mixture as a flux. So depending on what you want to prepare, you can change or tune the flux as well. So tin as a flux will give you the antiferromagnetic phase, and salt will give you the ferromagnetic phase. And ferromagnetic sample shows 1% European vacancy, and the TC is close to 26 Kelvin. And then we measure the notched effect, and it shows a value close to 6 microvolt per Kelvin, which is compared with the other uh, topological material. So other literature also shows that single crystal as well as the polycrystal sample can also realize the large transverse thermal power. So this is the summary of this series. You can see here, this is the Dirac semimetal, this is the Weil semimetal, and this is the nodal line semimetal. So you can see there are several reports on transverse thermal power, and that is maximum observed in WT2, which is a Weil semimetal. In case of Dirac semimetal, it is ZT5, and for RE4SI7, that is the narrowband gap semiconductor, shows the high non-thermal power. And now if you see here, this is the ferromagnet, antiferromagnet, and their either notched effect or anomalous notched effect. And you can see that for notched effect, the value is quite high because it requires high magnetic field. But till now, the anomalous notched effect is only 10 microvolt per Kelvin. So what is the future of transverse thermoelectric effect? Now, if you see the value versus temperature, in this temperature range, we have a high value, but in the higher temperature, we have a very low value. So we still have to find or do more research to find it out, get high Seebeck coefficient or transverse thermal power in room temperature. So we can be used for the practical applications. Now, very quickly, with 5 minutes, I'll show another applications of transverse thermoelectric measurement. As I have already shown this slide, and again, I'll focus on PBSNT material. Now, our goal is different. In this material, this is a rock salt structure, so it will need 6 bond to make the octahedral bonding. So you need 12 electron. But in this material, you will have 6 electron. So in this material, they are prone to rhombohedral distortion. So it will open up the band gap. Now, how to track that? So previous RPS or HTM shows that breaking of mirror symmetry. But for RPS and STM, you have to go to synchrotron, you need special facility or special expertise. So we thought, can we realize the same distortion opening in the band gap by simple measurement in the lab-based technique? So again, we focused on the Nernst effect. With that motivation, at Eisenhower, we have synthesized this single crystal. And then this is the crystal structure. You have a rock salt structure and it has a mirror plane. Now in this material, the cation and anion will move opposite direction and it will break the mirror symmetry. So it will open up the gap. So this is our idea how we can track that opening the gap. So then we did temperature dependent RP study because previous PVSNSE system shows that there is a change in the carrier from hole to electron. But when we measured our sample, we did not observe that. That means throughout the temperature, we have single carrier type. And then we did theoretical calculation and says that if our system has a distortion which open up the gap, it will have two topologically non-trivial pockets. So we can get that information from theory, but can we realize experimentally? So that's why we measured Seebeck effect and Nernst effect of this topological material, and we observe at low temperature several oscillation. And we know that oscillation can give information about Fermi surface, mobility, and so on. So we analyze the oscillation and we first subtract the background and then plot it with respect to 1 by b, and we can see clear oscillation of the Nernst data, and from that we did the FFT and we observed two frequency at 46 Tesla as well as 64 Tesla. Now our goal is to prove that these two peaks coming from the non-trivial phase. Then we do Landau level fan diagram fitting, and which confirms that the two pockets coming in this material are topologically non-trivial, which is actually confirming our theory. Then we did supporting information like experiment like Raman, again X-ray pair distribution function from the 300 Kelvin to 100 Kelvin, and it also gives an indication that there is a distortion of the cation and anion at low temperature. Then we did temperature dependent TM, and from that we observed that when we decrease the temperature to 94 Kelvin, we can see the start splitting of the peak. So you can see here from the TM, we can see different ferromagnetic regime, which gives the ferroelectric distortion. And then we measure the resistivity measurement in this sample, and we observe a large mobility of around 6,000 centimeters squared per volt second. At the same time, at the room temperature, you still get 1,000 order. So the quality of the sample is really high, and that's the why when you measure the resistivity, you can see clear oscillation of the sample from 2 Kelvin to 30 Kelvin, and then we did similar analysis and we observed two pockets coming from the topological non-trivial phase. So I'll skip this part. Yeah, so this is the last slide to the road to high performance thermoelectric. So it started in 1882 with Seebeck effect, and first breakthrough comes in 2006, where the nanostructuring increased the GT more than 2. And then after realization of topological insulator in 2012, people started working on anomalous Nernst effect. In 2021, we realized GT of approx 2.6 by using order disorder conceptualization, and hopefully in 2026 or soon we can design a topological quantum material which can show GT greater than 3.5 for practical applications. And with that, I'd like to thank you all for your attention. I'll just maybe stop sharing. Yeah, if anyone has any question, I can.
Yes, sir. There are queries actually,
Yes.
and there are compliments to you that it was really nice lecture. And
Thank you.
yeah, so from Ranjan Kumar Tung, he
Sir, recently, nonlinear Hall effect also came into the picture. Can you please share your comment about it? And is it possible to observe nonlinear Nernst effect in material systems?
Yeah. Yeah, so in Claudia's group, means from where I did postdoc, so they have started making the nonlinear Hall effect and start to measure. But the problem with the nonlinear Hall effect, we have to make the sample very thin. Otherwise, we have to, let's say, apply in 1000 ampere current, but that is not feasible in ppms if we want to measure in 1 mm thick sample. So that's why whatever report is there, they always measure in thin sample. So you can make the film in nanometer region and then you can measure the uh, non-linear Hall effect. Yeah, maybe in future we can measure non-linear anomalous non-stay effect as well. Yeah, but that is in process. And for that, we need a clean room to fabricate the device before the measurement. At the moment, in very few places in India, we have clean room, and maybe they are trying to do that measure.
Okay, sir. So one of the participant, Gopi, and actually is asking what is time reversal? Possibly you were referring to time reversal symmetry.
Yes. So time reversal means if you are going in a positive time, that means f function of t will be f minus of t. But we cannot go back to the negative time, right? So how to or understand the time reversal? So let's say I have a spin with a motion up and it rotates from right direction to left direction. Now, if I flip the spin, but now I change only the direction, but it still rotates from left to right. That means now it violates the time reversal symmetry because now they are symmetrically inequivalent. But if it flips and changes direction as well, so now their time reversal is protected. So if we apply magnetic field or magnetism, they will break the time reversal symmetry. But if you add some non-magnetic impurity in the topological material, they will still be topologically non-trivial because impurity level does not break the mirror symmetry, does not break the time reversal symmetry. Yeah, maybe this
Okay,
is
sir.
the physical way to understand a little bit of time reversal. Otherwise, there will lots of mathematical expression will be there.
Okay, yes. So this was the beauty of your talk that you skipped the mathematical part.
Yes.
So there is another query from Ranjan Kumar Tum that, sir, is it possible to measure Barry curvature experimentally?
That is difficult, but let's say as a consequence of Berry curvature, we can get anomalous Hall conductivity as well as anomalous Nernst conductivity. So theoretically, you will calculate the Berry curvature effect on anomalous Hall and anomalous Nernst, and then you can compare the measured one. At the moment, I have not that much clear idea, but I can look at the literature and get back to you that we can measure the Berry curvature. At the moment, what people do, they correlate the Berry curvature contribution on anomalous Hall or any other measured property. But I'll look into that. This is a really nice question. Thank you.
Yes, sir. So, in fact, uh, you covered many of the quantum materials which also have thermoelectric characteristics, prominent thermoelectric characteristics. And I think the very first quantum materials, so kind of well-known classical quantum materials, they are also well-known thermoelectric.
Yes, like BI to T3 or
BA to T3 and SB to T3, which are commercially thermoelectric materials, which are used in commercial thermoelectric devices.
yes.
So, just curious, can you comment on what is the connection? In fact, most of the thermoelectric materials are belonging to this class, or you can say other way around. Most of the quantum materials belong to this class. So, what is the connection between this topology or being the quantum nature, some quantum protection? How does it help in thermoelectrics?
Yes. So for thermoelectric, we need high Seebeck or high electrical conductivity and low thermal conductivity. So if I'm taking a heavy metal or chalcogenide, heavy metal or heavy element, so one side it will give a strong spin orbit coupling. So we can get, this is a topological quantum material. At the same time, we can get a low thermal conductivity. At the same time, these material are very narrow band gap semiconductor. So in this material, you can easily get band inversion, which is a criteria for a topological material. At the same time, you can get a large Seebeck coefficient. So because of their electronic structure and this uh, heavy element properties, we can connect that both the topological material and thermoelectric material, they share similar material properties.
Yeah. So, uh, another thing, this is somewhat similar query.
Yes.
This was relation with these, especially this one type of material where one heavy metal is used, like in transition metal disulfogenides or some topological insulators. We have this requirement of spin orbit coupling gives that condition, or you can say this heavy metal supports that this strong spin orbit coupling. But interestingly, such type of materials, they are also good at different type of other applications. Like chemical reactivity wise, I see many people use them for photocatalytic activities, catalytic activities. People use them for energy storage and uh, many applications, like graphene also, kind of one of the quantum material, and it has wide applications in different fields. So there also the link between being quantum nature and being applicable to this particular field is somehow not very elaborated. So is what could be the reason in your, I just need your views or comment on that.
Yeah, one reason for the catalysis or storage because it has a very high mobility. So there is a high chance it will be a good for that catalysis application. And because if there is some impurity or if you do doping, it will be still possible to get large mobility and you can get large electrical conductivity. So that's the reason maybe people are using for catalysis application. Another one is that you can tune the band gap in this material very easy way and still you can retain the non-trivial band inversion and so those properties that might be a connection. And now people are also working on spin, now that how the spin can change the catalytic properties with the magnetic field, and chiral crystal people are also working how the chirality change the game. So people are working in different region for different aspect, I guess.
So seems Rajan is really curious. So he has some more queries. Is
Yes.
it possible to have vary curvature in the material but not topology?
No, at the
Saying what?
moment,
Is it possible to have vary curvature in the material but not topology?
yeah, no, I think at the moment what people are mostly working, if it is a topological material, then only they will get the able to calculate the they will get the very connection, they will do in a closed loop calculation, I guess, and then they will get the very curvature information. So till now, I don't know any example where I'll have a very curvature but not topology. But vice versa is possible. You can get topology but you may not get very curvature. That might be possible, but at the moment I have no idea.
Actually, Berry's curvature, it was initially used to explain anomalous Hall effect. So it was introduced uh, earlier than basically this topological insulator and topological materials came into the picture. It is quite fundamental, the Berry's curvature. Okay, so the next query is, can you please make me visualize what is SOC actually, or what is spin orbit coupling? He just want some physical picture or physical uh, this description how we can relate this SOC.
Okay, this is simple Ellis coupling you can think. So whenever, let's say, you have an electron and you have to take an atom, so electron will rotate the atom. At the same time, electron will rotate itself. So when it covers the atom or the nucleus, you will get orbital momentum, and when it rotates around itself, you will get a spin momentum. So what you get a total momentum is the orbital as well as the spin angular. So then you will get a LS coupling that we call the LS coupling. So you will have a orbital magnetic moment as well as spin magnetic. And this thing you can realize mostly in case of a heavy element because they are heavy atomic number, so it can be proportional to that because spin orbit coupling is proportional to z to the power 4, I guess. So if the system has a heavy element or heavy atomic number, you will get strong spin orbit coupling. So you will have a more contribution from spin as well as the orbital. Yeah. So maybe that much, and then maybe I have to write some equation. Maybe that would be yeah.
Yeah, possibly maybe this coupling is a textbook kind of material. So if
Yes.
we can refer to some chemistry or physics textbook, then some more information can be there. And there are some other query also. Okay, so from Devans, if the surface states of topological insulators are protected against backscattering, does that mean electron moving through a TI essentially massless and heatless? If no scattering occurs, where exactly does the Seebeck effect come from a quantum level?
Yeah. I maybe understood little bit. So for the Seebeck or thermoelectric, you need little bit gap. So we have to break the mirror symmetry protection. That's what in the past example I told that PBSNT is not good because the bulk band gap is less than 5 electron. So we have to open the gap, otherwise you will get bipolar conductivity. So you have a major carrier and you have a minor carrier. So initially major carrier jump from valence band to conduction. But at the same time, the minor carrier can also transfer. So that will be detrimental for thermoelectric. And you are right, they will be massless. So that's why whenever we are talking about the opening in the band gap, you will see many literature, they found that there is a transfer from massless to massive fermion. So that depends on the materials property and what of your interest you want to study in those materials. Depending on that, you want to break the mirror symmetry or you want to keep it depending on complete what of your interest. Because if you want to measure Seebeck, we need to break that. Otherwise, it might not be a good candidate for thermoelectric application. Yes.
Yeah, okay, sir. Right now, no more questions I can see from the chat box. And yeah, it was really nice.
Yeah,
Although
thank
there
you.
was some break in between, but your
Yes.
slides and lecture were really nice, very pictorial, very you can say easy to take kind of material. And it was really necessary also because in the quantum materials, as I already mentioned and you highlighted that most of the quantum materials are Thermoelectrics, good thermoelectrics. So far we have seen. So I would like to thank you once again for accepting our invitation, sparing your time, and sharing the expertise with us. And yeah,
Yeah,
thank you
thank you, Sunil.
very much.
Maybe hopefully soon